Now we care about environment, right? We are all talking about trees.
Yes.
Okay,
Thanks for
well,
your point as well.
mm, it's so hard to see. Okay, after Lo present about the binary search tree, actually some advanced shape of binary search tree, we have some other like uh, balance binary search tree or red black tree, blah blah blah. It should be the same, but it have some mechanism to self balance from the left side and the right side to make sure the trees will not be very height. Yeah. So B tree is another shape of the binary search tree, or we can say that the binary search tree is the simplest shape of a B tree. I put it here because I copied this present somewhere. I don't remember, but yeah. So this is the agenda for this B3. We will go through this list. Yeah, then the first one, just learn about how the data is stored in the disk first. So this is the disk, but actually this is a STD disk, it's not STD. So the track is the circle here. And we have some definition here, but if you want to learn more, just read more about the disk. Yeah, okay. Then the next one, we introduced a new concept here called ISAM, the index sequential access method. This one, we will store M records on each disk block. The definition of blocks here, we have here. Then we use an index that consists of an array with one element of each disk block. Yeah, the idea is we store everything in the sequence, and then when we want to read it, we read all in sequence one by one. So this is we have a picture here to visualize this one. So we have an array here. We store this one in this point, the next one here, the next one here. But for this number, for the rest of them, since we have no room, so we have to save the rest of them in the next rings. It's not, so that is the problem. Sometimes will take more time for us to read the data using the ISAM method. Yeah, then to perform the get the element as the key index, we look in the index that we're using, and then we determine which this block should hold the desired record. Then we perform this set to read the block. Yeah. Then the limitation. So if the index itself is too large to fit the entire RAM at the same time, and also if when the insert and deletion, the block may yeah, maybe the block is too big, so it will cross the block boundaries. Yeah, this one, for example. Then if we want to improve this one, then we use B3, one of the solutions. The idea is we introduce a new concept here called M-way search trees. At Lowe's introduced the binary search tree. We can see that one node will have two leaves, right? But for M-way search tree, one node can have multiple leaves under it. So and we don't require that it should not always be full. So an element can be empty or can have multiple children. And the first part is the rebalancing mechanism. Yeah, so this one is the picture to visualize the B tree. So this B tree have the size of 5. This means one knot can have 5 leaf. This here we have 1, 2, 3, 4, 5, and it can hold 4 value. Yeah. Then then we have some operation can do with B tree. For this one, if we want to insert the 10 value, the same thing with binary search tree, but instead of comparing one element of the knot, we need to go through the whole element in the list here. So if we want to insert a 3, we can go through this list, but this list just have 12. So 10 is less than 12, then we go to the left of this element. Then inside this element, we search for this list as well. We go through from the left from the right, then we can see that the 10 is larger than 8, then we just simply put a 10 here. Then what happens if we want to put one more, like 11? The same thing. We look for, we compare the 11 with the 12 here, then we go from the left side, right? Then we look for this list. Then by right, we should put 11 here. But the size of this B tree is 5, so it can only hold 4 values. So we cannot put 11 here. Instead of that, we will put it in the leaf of the 10. So it should be the leaf, not the leaf path of this value in the red color here. But if we're doing that, the tree here will not be balanced anymore. So here we have the rebalancing mechanism, right? So we have to rebalance this tree. Then to do this one, we assume that this knot have 1, 2, 3, 4, 5 values. Then we will break it down into 2 smaller knots like this. We have 2, 3, 8, 10, and 11, right? Then we break it down into 3 here, then 10 and 11 here. Then we move the 8 to the top. Yeah, so now the tree is balanced. We don't need to have another external knot down here. Yeah, we have a lot of mechanism operation here, like removal. Yeah, a lot of cases of this, but I think we can skip. It's mostly the same with the binary search tree, but instead of comparing one knot, we should have go through the list values of the knot. Yeah. So after all, we'll summarize the performance, but actually we don't need to care. Yeah. Then summarize it. Actually, no need to care as well. So assume that we're done with the B tree. Then we introduce a new concept called B trees plus. The B trees plus is another data structure that's used to store the data. And it should be the same with the B tree, but the difference is store the data on the left of the nodes. We see here, we store the value of the nodes in the, we store the value in the nodes, but for the B tree plus, we store it on the left only. So yeah, it should be look like this. So all the value is here, and the 13, 13, 9, 11, 16, 38 here. There's none left values, and we will put it in the list as well. You see here the 9 here, 11, 16 here, and 38. They repeated the value. And from this one, if we put the pointer in like this, we set the pointer from 4 to 9 and 9 to 11, then the list will become like this. And using this, if we just use this list value here, we can easily do binary search tree, or binary search, normal binary search to go through this list, or we can originally search the same way with the B tree. Yeah, it seems like we have two solutions to go through this tree. Then, how the database use the B tree plus? For example, we have this table, including the name, mark, and age. So first of all, the database will create a Unix UI index. I didn't put it here, but it should have one more column called index. And then it will store, use some machine mechanism to convert it to the byte stream, and then store it to the disk. Then for this one, we convert it to the B tree, and we assume that we already have the index column here, right? Then this should be the index. We have this one. We have 1, 2, 3, 4, 2, 3, 6 record, right? And then we have the index here: 6, 12, 15, 24, 25, 53. Yeah, we use the index to build the B tree. We can see here all records are stored at the leaf node, and we don't need to store the record in the nodes, in the non-leaf nodes. Yeah, and we also have the reference to this leaf to the next leaf, and also one more feature that we can use, the database can perform the binary search if we use in the left list here. Okay. Then outside that, if we don't define the indexing, then the database will read each of the record to find the given record. Like it will read through everything. Then, but if we enable the indexing, then the database will create the B tree for each of the column here. Like we have where is it? We have 3 columns here, and one more column for the index. So by right, when we enable the index, then we should create 4 B tree to support the query. So this one is an example that we use the key as the name. Yeah, then that should be it. Is there any question?
Very technical again. Anyone have questions or things to add? Like you actually know more about this topic, how the index being done in DB, or how B-tree, like how B-tree compared to BST, for example, like why people come up with B-tree. It's really technical, I assume. Or you actually know more. Do you know actually like how efficient B-tree compared to BST? Why is it n-way tree the final way people do instead of just binary?
The first of all, the B tree is a bit hard to store in the disk. Like it's just one not just have one value here. No, it's not the binary tree. But yeah, the binary tree just have one node. Then it's not in sequence. It's a bit hard to store in the disk. So, but in the disk we have the list of the elements, right, sequentially. So by right, we should define a size of the B tree. Then when we store it to the disk, the way we read it will be faster. Yeah, and by right, this is just an example that the size of the B tree is just 5, but normally the size should be bigger, like 1 to 8 or 5, 1, 2 or something. It's very big. So if we use binary tree here, the size is very, very big. Like,
right.
but we use B tree, then it just have the sum level of them.
Right. Yeah.
We can reduce the size.
Yep. Yep.
Yeah, but we can still keep the benefit of the binary search tree.
Correct. Yeah, I agree. I think when I study, I also remember B-tree, like the major point about people using it for database is about the sizing. Using a binary tree for doing the index for DB, like the size will become very crazy. But then if you use an n-way B-tree, the size actually greatly reduced, so as the height. And then if the height reduced, the performance also is better. Then actually there's a formula to calculate what's the optimal size of that tree. So you cannot do it like in 100-way B tree, right? Basically, like it becomes linear again, like you lose a tree structure, it's too flat. But there's a structure you can try to fit into the hard disk. So if the hard disk one of a page size or the track size is, let's say, 1 kilobyte, then store 1 kilobyte. Then actually you try to make each of the node here of your tree as large as 1 kilobyte, something like this. So you actually fit to the hardware as well. That's why it becomes very low level and technical. Okay. KB tree. Anyone got any other questions curious about B-tree or BST before?
I'm just curious about what's the performance difference between like BST and B3 plus, because like BST is they compare the two nodes beside it first, but then like with B3 plus, how would the traversing of the tree be like?
This one will be a bit slower comparing to the binary index tree. Binary search tree, I mean. Because it is stored in the list, right? So you have to go through this list. So by right, it's not O log O anymore. It should have to time the size of the B tree as well.
Okay, got it.
We have the performance sum here. Okay, here. So it depends on the height of the B tree.
B3, yeah, your B3 plus will be a bit different. I think for B3 and BST, it would be similar methodology, but your B3 plus will have some redundancy and also like your leaf node. They actually store some redundancy for other performance to be faster. So this time if you go B3 plus that one again, like then you see that the leaf nodes can be itself become a list in ascending order. So like you see the data storage point of view, like it's better, and then the traverse time, for example, finding predecessor and also successor, this time is much faster. So when you compare performance, I think like you have to talk about the different operation. So there's no general performance which one is faster, but which operation we kind of sacrifice or you have to trade off, balance out. If you want to find successor faster, then this one is faster, but we also use a bit more memory and increase a little bit of the height. Then in other words, like some other general search function becomes slower. So it's a trade-off. It's quite typical, like these kind of data structure all have different trade-offs.
Okay, got it.
And do you guys know HIP? Like, yep, do you know HIP?
You mean HEAP?
Yep.
Oh yeah, yeah.
Yeah, it's another kind of binary tree structure. And that one has a fast performance on some of the operations that Lo just mentioned. For example, the min and max will be very fast. It will be all one, like it's a constant time. But some other operations will be a bit longer, kind of thing.
Okay, understood.
Wait, so why do we, like in the B3 plus, right? Why do we connect the leaves together again? Is it purely for redundancy purposes?
It depends on the usage. If you don't need it, then then you don't
So
need it.
So it's
we
like-
have, if we don't have it, now we have only one way to go through this tree, right? We go from the
okay,
top.
right. So it's like there's another way for you to traverse the tree, basically.
Yeah.
Okay.
Yeah, that is one benefit. If we don't store the record in the left, so we cannot do that. Yeah, I think.
Yeah. So the last line explained this thing. I think database can perform binary search or sequential search. In a sequential search, you go to the leaf nodes only.
Yeah, I think that should be it.
Okay, cool. Thank you both. Very technical this time. See whether we have other topics for other areas in technical and non-technical next time.
Okay, thank you very much, guys. And that'll be it for this week. Thanks to Ibrahim for joining as well. Yeah, so welcome to the team again. Since you're here, might as well say welcome.
Yeah. Okay, we'll break a few minutes. And I think we can go to the polling session. Wait, what is it this time?
It's a yes/no game. Basically, Johnny will be showing you guys some questions, like a riddle. Yeah.
Then we will do it later. Okay, thank you.
Thank you very much. Bye, guys.
Bye.
See you later.